Okay, so today, well, what looks like 3 topics is really just 2 topics. Metadata first half of the lecture, metadata. Second half, data warehouses and data mining. Really, the lecture is, or the second half, the main content is on data warehousing rather than data mining, but they kind of go together to a certain extent. So we'll just scratch the surface of data mining. The main emphasis is on data warehouses. So first half, probably try and keep it relatively short. Metadata, rather wonderful t-shirt produced by the British Library. Metadata is a love note to the future. You write metadata to make data. Metadata is about making data accessible, reusable by yourselves, but by other people. And if you put the effort, if the metadata is not prepared carefully and with love, it's of only limited value for enhancing the reuse of data in the future. Oh, dear, that was a bit of a... Right, where's page up gone? Okay. So, metadata. You're familiar with the idea, at least the basic idea of metadata, I hope, which is that it's classically, or the normal way of describing it is data about data. Because, why do we need data about data? It's because in most things in life, context is everything, including data. If you don't know the context in which data is collected, it is difficult to understand its errors, its good points, its benefits, its bad points, and determining whether it is fit for use, because ultimately that's what, when you're trying to find a data set or collecting a data set to undertake a particular task, you need to decide whether it is fit for purpose or not fit for use. And the metadata is the first stop for deciding whether it is suitable or not, or it's a good place to start. What is metadata? Well, it's structured information that describes some kind of resource. And I don't say data set there because there's metadata that goes with data sets, there's metadata that might go with programs, there's metadata that might go with services, there's metadata that might go with individuals, people. So a resource of some kind, whatever it is. And basically, the types of information that it contains is the who, what, where, why, when kind of questions. If we're talking about data sets, geographical data sets, who collected the data set? What does the data set actually contain? Where is that data set related to? What part of the Earth in geographical data sets? But also where the who are, so to speak. When? Does it cover a particular time period? Is this an ongoing data set? Is there ongoing collection? And the how. How was the data set collected? Because that obviously has implications for the quality of the data set. A crowdsourced data set has different qualities to a highly structured, governmentally led data collection exercise. Say something like the Ordnance Survey used for updating their topographic maps. The other thing to notice, to know about metadata is that there's kind of 2 types, or you can think of there being 2 types. There is metadata for people, us, that follows roughly natural language. So we like natural language, we read paragraphs, we read sentences, etc., etc. So there's metadata that's designed for the consumers, the people consumers. There is also metadata that's for machines. So machines want to know something about the data set that they're accessing. There may be metadata which is formatted more for machines than it is for human readability. So there are these sort of 2 types. Often this is a continuum. A paragraph of data is obviously natural language, but a value in a field could be regarded as either of them. To a certain extent, is how easy you can access that. So, 2 types of consumers. Okay, really just quick few slides. What is metadata used for? What do we use it for? What's its purpose in life? Probably its number one purpose, or the most common purpose that we think about, is resource discovery. You want to find some data about something. The metadata helps you find that data set through things like, obviously, its title, keywords that get associated with a data set, things like that. That helps you discover it. And then when you found a data set, or at least by the main keywords, sort of an initial crude search, you can start reading the abstract, the data description, metadata, to get a sort of bit more in-depth information about that data set. And without that information, it's obviously quite difficult to, you may have a variety of data sets, similar data sets about the same thing. You want to decide whether you can bring those data sets together into a single data set. The metadata is a good indication about how much those data sets differ and how much effort would be required to integrate those data sets into a single resource. So, discovery and understanding the data that's out there. Metadata is used to support and implement interoperability. Interoperability, remember, is the ability to take data sets, different data formats, and be able to read them in multiple types of software, to be able to access data, say, stored in the R statistics program from ArcGIS, vice versa, so that we can use tools from different systems on the same data sets without needing to undergo sort of manual conversion between formats and things. So if the metadata describes the data set and how it's formatted in and what kind of digital container it's within, then potentially that metadata can be used by, say, another software system, comes in, interprets, accesses the metadata, discovers what the data set is, then it knows how to read that data set into the software. So interoperability is, the metadata enables software systems to communicate among each other without us as users needing to tell it necessarily what to do. We've also seen, we've talked about standards, not in relation to metadata, but in relation to data models and things like that. Clearly, if we use similar metadata standards, then that enhances our ability to exchange and integrate data sets between different organizations. Where we do have different standards, and we'll talk about standards in a minute, then we need potentially to map, for it to allow interoperability, we have to map fields and things between standards. We'll see that in some examples later on. What else is metadata used for? Digital identification. So we're going to sort of, we're starting to a certain extent to think about things that we're going to deal with next semester when we go out into the internet. So one of the big problems in managing data is knowing whether the data item that I have and I'm holding is the same as the data item that you have wherever you are. So we've got copies, multiple copies of data sets all around the world, versions of the different data sets. How do we know we're talking about the same thing? And one way we can do that is by assigning unique digital identifiers to data sets, data records, and other data items. So basically, or a form of metadata is unique resource identifiers that unambiguously identify something in the internet. One type of identifier is called a GUID. You may well have heard of these. Globally unique identifiers called GUIDs. You'll have seen them even if you don't know what they are. When you install programs, you need a program license. They are often GUIDs, or certainly used to be. So they're often displayed as 32 hexadecimal digits. Remember, hexadecimal is just binary in being displayed in the base 16. So this is in fact a number, despite the fact that it's got letters in there. Basically, there are so many numbers in this number that we can generate these randomly, and there are so many that the chances of us ever generate, anybody on the Earth ever generating the same number twice is very, very, very tiny. So effectively, we're picking numbers out of such a large number pool, a number pool which I believe is far larger than the number of atoms in the universe. We're picking out these numbers. They're almost guaranteed to be unique for hundreds and hundreds of years of us picking numbers out, millions of these numbers every day, trillions potentially of these numbers every day. So it gives us these unique numbers, very high. They're possible to be duplicate, but highly unlikely. And we can these are used quite a lot in databases to uniquely identify rows. So there will be a GUID data type in Postgres, so that we could assign a GUID to every row, and then somebody else makes copies of that rows. They go around the planet. 2 years later, you want to know, is this the same row as you had? As long as the GUID matches and no data, other data in the row has obviously changed. If there's not been any data editing, then you can say it's come from the same locations. It matches. And this is particularly useful for maintaining. We had a bit of a lecture on distributed databases. Not my finest moment, perhaps, but it's the way that distributed databases, or one way in which they maintain the uniqueness of rows, because you've got multiple copies of the rows in distributed database. Add the GUID on, and you know where you've got copies, basically. The function of metadata is to make sure that data is archived and preserved correctly, and that people know how it's being archived and preserved. So digital resources are fragile. They are lost. They are not. They can be lost, especially from some old data sets, for example, from the 1970s, 1980s, stored on old hardware that's no longer, it's actually difficult to get readers for. I mean, one point I was handed a tape disc that looked like something out of a Harry Palmer movie from the 1960s. You know, one of these things that you used to see with giant double reels of tape and stuff like this. They're still out there. They're not very common, but they are still out there. Floppy disks. You try finding a computer that will read a floppy disk nowadays. Do you know what a floppy disk is? Even first years probably don't. I expect you lot know what a floppy disk is. Quite a lot of our first years have never seen a floppy disk in their life. So beware. They do, yeah. These stuff all degrades. Even CD-ROMs degrade and things like this. You know, they are not permanent.
I know when I worked for council, they'd already found that some of the things on floppy disks were already unreadable, whereas things on the magnetic tape from the 60s
Still good, yeah. So this is and archive stuff gets stuck on boxes, stuck on shelves in the back of cupboards, and they're found 20, 15 years later when somebody needs them. So, you know, so this is a problem. This isn't just it is a real problem. Okay, there's also problems about things like some software only runs on historical operating systems and something like that. So if you're trying to reproduce a piece of work done 30 years ago using software from 30 years ago, you may actually have a trouble running it. And so the metadata will describe, for example, the operating systems that software has to run off and stuff like that. Also, archiving and preserving, we've got an issue. Data sets change through time. Some data sets are created and they're effectively static. Others change through time. So how do we use the metadata to understand how a data set has changed through time? Okay, quick. I don't want to spend too long on this. Metadata categories. So a lot of this, and indeed that previous list, came off this site, the dcc.ac.uk, and if I remember correctly, it's the data. It's basically the National Research Centre for Digital Data in the UK. I can't remember what its full title is. It's a good site. It's well worth having a look. Anyway, they list the types of metadata. Okay, so the previous list was what you use metadata for. This is the different categories that exist within a metadata record. So we have 5 different categories that they identify. I've seen many other different 6, 7 lists, you know, constant category. These categories, we all draw up a slightly different list. So the first type of metadata they list is descriptive metadata. This is what we're all familiar with. Data about data, or content about content. It tells us about the data set and potentially individual items of data as well. So it includes your classic title, abstract, author, keywords, etc., etc. And this is what we use to identify and retrieve information resources. It may also include, should include controlled vocabularies for fields. So if you've got only certain values entered in particular fields, it should list these values. Very simple, descriptive metadata, what you're used to. But there are all sorts of other types of metadata which, you know, most people are not familiar with or don't have to deal with on a regular basis. So there is what they call technical metadata. This is both for humans but also for machines as well. And it is described there as data about the containers of data. So what format, so what format is the data stored in? Is it in a flat file, a shape file, a relational database? What's the structure of the relational database? Is it an object database, etc., etc.? So it's the design and format of data structures and schema that store that data. Also may cover the technical processes used to create the data. What instruments were used, if instruments were used to record, say, water quality or sort of, you know, dissolved oxygen in the water, how was that measured? And that, because that impacts on the accuracy of the records or the precision of the records. I've never quite, technical requirements to use that data, not quite sure what that really means, looking at it now. But I guess, you know, if it was only readable, if it was a file geodatabase and it was only readable by a particular piece of software, that may be a technical requirement, I suppose. Third type of metadata, administrative metadata, how the digital object is managed, who's the owner. This is one of the things, all data sets should have owners. Who owns that data? Who manages it? Who looks after it? What are the intellectual property rights? Is the data owned? So quite often data is owned by multiple people, but it is managed by one organization. So 5 organizations may be in partnership to collect the data set, but one of those organizations holds it and manages it and looks after it, so they may differ. License conditions, what can you do with the data? Can you use it for commercial product? Can you sell it? Can you resell it, repackage it, resell it? Or is it an open, free, everything you have to do with the data has to be free? Can you use it for commercial purposes? Can you use it for academic research? Those kinds of questions. We'll talk about licenses as well probably next semester. How to cite the data. So data citation, something students are pretty awful about, and probably one of the reasons is because they, I don't know, as part of your research methods module, you'll have covered citations. Have you covered citations yet? Well, when you get there, you'll cover citations, but they probably won't mention data citations at all. If they certainly didn't 5, 10 years ago, hopefully they should now. Something that I'm constantly finding, I go to student work, not just both at master's and undergraduate level, and the people have said, I got the data from X, and they just write in something like the Environment Agency. But they haven't given you the full title of the data set, they haven't given you the URL, they haven't cited the data properly. So it's important that you learn how to cite data sources. And things like version control, what version of the data set are you on? Use metadata. This is for use by the data owners, really, and it's things like what access to the data set, who has access to the data set, is it public, is it restricted to certain people? They may involve use tracking, how many people downloaded the data set, who were they, did they need to, require people to register, or are you just counting the number of downloads? So that kind of usage. And you may want to partition that by the different versions of your data set as well. So use metadata just basically tracks who uses your data and who's right. Final one, well, that maps onto our fourth one, preservation metadata, what actions are taken to preserve the digital object, what migrations occur between perhaps format versions, updated versions of data sets. Data sets are constantly being reissued, updated. What physical media is it provided on, if it is provided through physical media as well as digital download, and things like checksums. Now, I don't know much about checksums. They're basically big numbers that are calculated and then basically make sure that you've downloaded all the data. If your checksum matches the checksum that's published by the publisher, then you know that all the data has been downloaded correctly. Checksums are also used to check whether software has had viruses injected into it. If the publisher, when the publisher compiles the program or publishes the program, they publish a checksum, and then if the software that you download has a different checksum, you know something's happened to it on the way, and that may be the injection of malware and things like that. So, not an expert on checksums. There we go. Okay. Levels of aggregation. Metadata is usually at the data set level. Now, I think next semester we'll talk about what a data set is, as opposed to data and things like that. But metadata may be applied at any level of data aggregation you like. So there may be metadata associated with a database in a relational database. So at the database level, it may exist at the table record level, the record level, the attribute level, the values, relationships and constraints. All these objects, all these parts of the relation model may have metadata associated with them. It's quite unlikely. You usually get it at the database scale, the table, and the attributes. You may get it at the record level as well. Relationships and constraints are probably quite unusual. But it is possible to have metadata associated with any level or aggregation of your data. How is metadata stored? Okay, there's two places, basically, either internally to the digital object or in an external file. Those are your two, or externally. So, embedded in digital objects. So images and some sound formats, so JPEGs, PNGs, TIFFs, RIFs and WAV files, have a header section which stores metadata associated with that digital object. And image formats and sound, quite a lot of these formats store their metadata in what's called the exchangeable image file format, EXIF. So the EXIF metadata is embedded within the JPEG file, for example. And this is how you get things like geocoding of JPEG files and things like that. You take a photograph with your digital camera, you've got a GPS associated with it, it automatically downloads the coordinates. Those are embedded within the file itself. Perhaps the date as well, and think the date and time of the photograph, that sort of thing as well. So that's actually physically embedded in the file header. The other place where you get this kind of thing is HTML header tags. So HTML, hypertext markup language, the language of the internet. What is the internet is written in. So we'll meet that first thing next term. So HTML web pages have metadata embedded in the head, what's called the head component of the table, of the page. Then we've got some kind of record that's separate, physically separate from the digital object, and that's the more common situation, certainly for data files as opposed to images and sound and things like that. So either stored as some kind of database records or in an XML format. What's XML? We're meeting a whole load of new things in that we're going to see in detail next semester. XML is extendable markup language, and it is a language for specifying data. We'll actually see it in a bit. So internal, external. Metadata is formatted just like data into some sort of schema. So we have a set of metadata elements, fields basically, that store our metadata. And these fields are designed for storing information about a certain type of data. And those schema define the metadata elements, basically the fields in your metadata schema, and also what type of data can go into those fields. It's data just like temperature data or anything else. So the element domains cover things like the data ranges, vocabularies, syntax, things like whether you enter things capitalized or not. And then it also defines the ordering of the fields, the metadata elements, in the data format that is stored in. So the ordering of the metadata elements in an XML, GML, or whatever format these elements are stored in. Just like any data can be stored in any database model, we can store any metadata schema and elements in a variety of syntaxes, in a variety of formats. Metadata standards are just like data standards. They're agreed schema for storing metadata. So, the mother of all metadata standards for digital objects is called Dublin Core. Dublin Core was devised primarily, this is Dublin, Ohio, not Dublin, Ireland, a meeting in Dublin, Ohio, organized by the National Supercomputing Center in the US, I can't remember, 1995. And they brought together a whole load of different people, a lot of them from the library community, to develop a metadata standard for all digital resources on the web. So this is a kind of overarching schema that's meant to cover everything in a very general fashion, particularly for the library community. So it's again managed by one of these consortium. In this case, it's the Dublin Core Metadata Initiative. And the sorts of fields that it defines are things like title, creator, subject, description, publisher, contributor, date, type, format. We've got a whole list of them there. But you can see that these things are very generic items, data objects, and they could be related to a data set, a film, a piece of music, a photograph, an object of art, just about anything that could be on the internet, a web page. All of these, most of these metadata elements are very general, can relate to any type of digital object stored on the internet. So it's a very high-level standard. Well, that's great in that we're all hopefully using the same title field, description of a title, description of a language, description of a format. But clearly that's very general. And most, when you're working in a specific area, there's lots of other types of information, metadata information that you're interested in. So what happens is that individual domains, including the domain of geographic information, create their own data sets based on the Dublin Core and other general schema, and expand them out to meet the specific needs of in their domain. So for geographic data, there are a variety of spatial metadata standards defined, including an ISO standard, the EU Inspire, I think it was created with a directive, European Union directive, which is the effort for the European Union for reporting and basically to get a standardized data sets across the entire of the European Union. You need common standards so that they can be brought together, the individual country data sets can be brought together at the European scale and integrated to create European scale data sets. So the EU Inspire, so EU Inspire is used by the European Union. The UK government has a standard called UK Gemini, and clearly when we report to the European Union, not that we're going to do this for that much longer, I suppose, we have to map our UK Gemini standard onto the EU Inspire standard to be able to exchange metadata with the UK metadata with the EU. In America, the federal government defined the FGDC, which is a very widely used standard, Federal Geographic Data Committee standard. But metadata standards exist in many other areas. So the area I work in, being a sort of biologist, ecologist, whatever. So we have another metadata standard called ecological markup language, which is specifically for ecological data sets, studies of blue tip mating in Berkshire, all this kind of stuff. There is also one called Darwin Core for natural history specimens held by museums, which has also been expanded now to species observation records. So somebody goes out, sees a lesser spotted something through their binoculars and records the location, and then it's supplied. Once it's been entered into a data place, it's then the metadata is in Darwin Core. So as I said, Dublin Core, I call it the mother of all standards. Other standards take as much from Dublin Core as they possibly can, usually all of it, frankly, because it's designed to be a very generic system. Then they add in new metadata elements which are specific to the subject that they're in. And wherever possible, which standards, when they're defined, should reuse elements from other standards wherever possible. So the ecological markup language has a section on geography, because the geography of where the study was done is very important. That geographic component of EML borrows fields from the geographic standards. So it uses they went away, they looked at what standards there were for geographic data, took those and used them in the ecological markup language so that we can then map from EML geography to ISO geography. Oh yeah, just a list of people who use FGCC. It's widely used in the US. Okay, I think we can skip this. So FGDC breaks it down into a different set of metadata fields. We don't need to worry about those. Gemini, really quickly. Okay, so here's Gemini. Gemini, I understand, is the UK government spatial metadata standard. And this is from the documentation here. So here's the metadata elements, listed 1 to 43. We've got a name for each element. As we can see, some of them are spatial, some of them titles, topic categories. These are all the fields. We've got a list of whether they're obligatory or not. M for mandatory, C's and M's, C's and O's. I don't know what the difference between an O and a C is. Anyway, 3 different categories, mandatory, non-mandatory, and something else, which we're not quite sure what it is. I'd have to read the standard again. And here we've got the number of occurrences. So there is only one title for each record, but there may be many alternative titles. There may be many data set languages. So for example, a data set may be supplied in both Welsh and English. So either one or many relationships between the element and the number of items that go with each element. Okay. So title, here's an example of the title field, the title element, number 1, name given to the data resource description. what I wanted you to see here is here's the equivalent Inspire element. So it's the mapping between the Gemini format and the Inspire, the European Union Inspire element. And you can see that it's called title in UK Gemini, but it maps onto resource title in Inspire. Then we've also got a mapping onto the ISO element, and we can see that it's equivalent. These two fields are effectively the same. Why are they the same? Or they're the same. So the ISO, data identification citation title, is the same as resource title in Inspire, which is the same as title in UK Gemini. They all probably are. Where do you think they come from? They come from Dublin Core. They all come from Dublin Core, and that's why they're all called the same, but they've been given slightly different names. Gives you eGems, so the whole mapping onto a whole load of equivalent ones. It tells you that it's a string. It tells you that it's free text. You can put any text you are. Basically, it's the definition of that element. Category, I'm not going to go into these in any detail, but this is going to give you, we can see that this is a class, and we can see that the valid values that go into this field are the same as the listed in the topic category taken from the ISO list. So we want to know what values can go into this topic category. Well, they're these values from the ISO list. Categories out, and there are the categories. We can see these are the topic category list. And it's got some details of them there. Extent, blah, 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 yeah. Okay, I think we can go through those. Now, so there's all these lists, all these fields to fill in. It takes a lot of effort to fill in metadata records properly, which is why quite often they're not done by people like myself, for example. Guilty. Okay, lineage. Lineage, I just want to stop on lineage. Lineage is UK Gemini, again, we can see, and it's free text, and it says some sort of information provided, including statements of the following source material processed to create the data. So this is a description of how the data set was created. Now, lineages, if you think, have you met Art Model Builder yet? Yes, Model Builder? Yep. Okay, so a lineage, a Model Builder workflow is a type of lineage. It's how it explicitly records how a data set was created. Don't worry about this one, it's a heat map visualization. But basically it's telling you what data went in at the beginning and explicitly defines all the processes that were used to create the data set at the end of the day. So the lineage in the metadata is a textual description, but what we're slowly working towards, I think, is the ability to store these workflows as the lineage rather than having a sort of natural language description. We probably want both, but if we can store the lineages, these workflows, these explicit workflows as part of the metadata, then we've got an explicit record of how that data set was created from other data sets. There are developments in progress to create workflow standards for eScience, but they're still in early days. So lineage is one of these areas of active development at the present day. Good old KXCD comics. Situation. There are 14 competing metadata standards. So I just showed you 4 of the geographic data standards. There are many more. Duh. 14, ridiculous. We need to develop a universal standard that covers everyone's cases. Yeah. Situation, there are now 15 competing data standards. It's virtually impossible to get everybody to play the same game. Part of this is just history. People started doing things slightly differently and they've got their systems set up for a particular metadata standard. Then it takes them effort to change, but it's not, the benefits aren't seen to outweigh the costs. The other thing is we all just have slightly different needs and different emphasis. So, for example, we are far more concerned with commercialization of the data, of government-collected data in the UK, or certainly were 20 years ago, than, say, the Americans. So, yeah, the basic take-home story is you'll never get one metadata standard for everything, everywhere, for all people. There's just too much diversity in the world for it to be done. Quickly finish off the metadata. So I've talked about what metadata is, but now how do we actually store it in databases? Well, one of the things about metadata is it's quite hierarchically structured. So if you remember, we had those list of elements for UK Gemini, and then we had multiple elements, instances of some of the elements underneath. So that's a very flat, but it's still a hierarchy. It's a very flat hierarchy. Each element can then have more than one sub-element to it. And so it's hierarchical. It's structured hierarchically, and it's also sparse. What do we mean by sparse? It means there's a lot of missing data items. So lots of fields that aren't filled in potentially. So as a combination of it being structured hierarchically, relatively sparse, and involving a lot of natural language that humans need to interact with and be able to read, what happens is that a lot of metadata is encoded in this XML format, extendable markup language, and is stored in what we call XML databases. Now, XML databases can be everything from a set of raw XML files. XML is just a text file. This is an XML file on the right-hand side. It's just a text file in which the values, in this case Canadian ICE service, are enclosed within tags that define the name of the field or the element in the item. So this is the origin of this data set is the Canadian ICE service. The publication date is 2008, 03, whatever. So these tend to be stored in XML format, and that XML format there are dedicated databases designed to storing XML. You can also store XML in relational databases with extensions, just like there's an extension for Postgres, there's an extension for XML for Postgres. There are a variety of ways you can do it. Metadata in ArcGIS, hopefully you've seen this. You get the data set in the catalog, you find a data set, you then in catalog there's a description tag, and this allows you to enter metadata into ArcGIS and it's stored within ArcGIS system. And if you right click, I think, and go to the properties, the options, you can choose whether you're going to store it in Inspire format, FGDC format, whatever. And I think this will do the mapping. So if you decide you're going to change the format, it'll do the mappings between the various fields. So it'll reconstruct the data set, metadata, in whichever format you want. There is also for UK data, there's an online metadata editor that allows you to enter the metadata fields and will turn the XML to you for usage. Really quickly to finish, just to remind you that metadata is data and can be used like data as well as for discovering things and for managing data sets. It can also be used as data in itself. So I love this kind of stuff. This is great stuff. So what this is a map of science. What they've done is they've gone to one of the bibliographic databases, one of the paper databases. They've extracted the metadata for huge numbers of scientific papers. They've mapped the topics from the keywords on the papers, and then they've basically done a network analysis, network clustering of those papers on the basis of similarity of keywords. And this is effectively a map showing the connections between different sciences. And we can see that biology is closely connected to earth sciences, but earth sciences, for example, virtually never publish with the social sciences, for example. They're very separate in separate conditions. We can see this wraps around social sciences, map onto maths, physics, and we can also see that different ends of the physics are used for what you could call your harder sciences, although I don't think that's a good way of describing them, but your geologies and your biologies versus your humanities on the right-hand side. So that's an example of the use of metadata. Here's another one, a geographic use. Again, this is in fact scientific collaboration, so the similar data set, but instead of being mapped into a space of subjects and similarities of subjects, we've actually got a geographical map, and this is the strength of scientific collaborations between different organizations. It's a bit of a hairball diagram that it's difficult to see anything in, but it's an example of where metadata is used. Really quickly. Okay, so there is also, it's gone off the boil a little bit when Snowden defected, ran away, released the WikiLeaks and all this. There was a whole plethora about metadata and phone calls and things like that in the news. So I thought this is just a nice little story about metadata and the sort of the power with which metadata, things that you can do with metadata, in particular regarding security and personal security. So this guy, Todd Seidsma, how do you pronounce the man's name? That's our Nordic speciality. Wrong language, okay, fair enough. But yeah, from the, you've got to know these things, the general vicinity. Okay, Tom Seidsma, doesn't matter. All right, he had his mobile phone. They grabbed a week's worth of metadata off his mobile phone. This is the type of things that security services do all the time. Phone usage, email header information, geolocation tags. Okay, so they took a week's worth of his data off, 115,000 times sampled records. Every time he sent an email, visited a website, we could see when this occurred and where he was at that moment within a few meters. We were able to infer a social network based on his phone traffic. So these are the sorts of things that they discovered just from the metadata on his phone. They worked out he's a recent graduate in his 20s, receives email about student housing, part-time jobs. He works long hours. He often doesn't get home until 8 o'clock in the evening, useful if you want to break into somebody's house to find documents or plant some evidence, something like that. He continues to work late. They're not sure if he lives with his girlfriend, but they do know he spends an awful lot of time talking to each other online, like cycling. They know his sister's name, they know what books he reads, and he knows what kinds of searches he does on the internet, not surprising. From a marketing perspective, he looks like a good potential person to advertise Groupon and other computer stores. He does lots of shopping online and doesn't see the need to unsubscribe some newsletters. Could be a good indication that he's open to considering online offers, so get that spam in Todd's direction. Political leanings. We think he sympathizes with the Dutch left, although he's always in contact with other parties. So we think he's a green lefty. We know that he's interested in technology, information security, privacy issues, and internet freedom. So we know the sorts of things that he's interested in. We know exactly where he works and in what capacity. And then this is the frightening bit at the end. Adobe had a breach of, and 150 million passwords were downloaded. These passwords were encrypted, but the hint question was not encrypted on the hacked email, the password list. Okay, so the analysts saw that some users had the same password for Tom because the encryption gave the same value. So multiple people have the same password because the encrypted value is the same. You don't know what the value was that was encrypted, but people share the same value. So they then looked at the password hints from these various people with the same password as Tom's and discovered that they included things like punk, metal, astro, lux. And this led them to break his password and strung out his favorite band. So despite the fact that he works in computer security, he's pretty lousy at it himself. They got his password, they broke into his Twitter and Google accounts, and they could have started spending his income on buying books on Amazon and things like that. So let that be a lesson to us all. Okay, that's a lousy slide, metadata summary. That's garbage. But so basically, metadata covers these descriptive, has a variety of functions, facilitates interpretation. And be warned that the metadata is data. You can do whole studies on metadata. It's just the same as data, but it just happens to be data about data. Okay, so we'll have our break. Oh, God, we're going to run out of time again, but never mind. We'll have a break, and then we'll go into data warehousing and see how far we get on that.